Okay, now let's turn our attention to 8.2, which is the second part of AP Calculus, topic 9.1. So we're still talking about parametric equations, but now we're going to talk about how to differentiate them. And for this lesson, we're really just going to focus on the first derivative and thinking about what that means. So let's read a few things, and then we'll practice a few problems. So the derivative or slope of a plane curve is found by this. The dy over dx, or the slope or the derivative, is the derivative of y with respect to t divided by the derivative of x with respect to t, where the derivative of x with respect to t cannot be 0. That would be not continuous at that place. Now, if the derivative of y with respect to t is 0, the y, then that is a horizontal tangent line. Now, we can have the derivative of x with respect to t equals 0. It wouldn't be continuous at that point, but it is a vertical tangent line. No, we're going to start all over. Okay, now let's do the next part of AP topic 9.1. This is lesson 8.2, and we're going to look at differentiating parametric equations. So here we go. The derivative or the slope of a plane curve is found by dy over dx, which you're going to take the derivative of y with respect to t and divide that by the derivative of x with respect to t. And whenever we're talking about slope, particularly, the derivative of x cannot be 0 at that point. Now, if we just set the y part equal to 0 and find that, then, if the derivative of y with respect to t gives us 0, that is a horizontal tangent line at some point in our plane curve. And if the derivative of x gives us 0, then that is a vertical tangent line somewhere in our plane curve. But it's important here on number 4 that a plane curve cannot have both derivatives equal 0 at the same time. Something weird would be going on there. Technically be a point. There'd be no movement there passing through time. So let's actually practice those ideas for a second, and then we'll look at a little bit more that we need to know about this lesson. So here we go. Let's imagine we have an x function based on the parameter t, and that's going to be 4 times 2t plus 1 all squared. And then we have a y parametric equation based on t, and that's going to be equal to 6t squared. So if we're asked to find the derivative of x, or y in respect to x, we're going to find the derivative of y with respect to t and divide that by the derivative of x with respect to t. So let's take the derivative of y with respect to t, and that will give us, 12t. And then let's take the derivative of x with respect to t. So let's see. We have a little bit of chain rule work to do here. And so the derivative of the inside, 2t plus 1, is 2. And so let's write that there. And then we have the constant 4 in front, or the coefficient actually. And then the derivative of the squared is bring down the 2, and then we have the stuff on the inside, and we lose a power. So that is now to the first power, which I'll write there just to show you that we did it. So we can simplify dy dx now in respect to t. That'd be 12t over 2 times 4 times 2 is, let's see, that's 16, and 2t plus 1. And we can reduce the 12 and the 16 and get 3t over 4, 2t plus 1. All right, so that is the derivative of y with respect to x of these two parametric equations where t is the parameter. Now we can use that to find specific slopes along the plane curve by plugging in specific t's, right? Specific times. All right, now number 5. Well, no, I'll tell you what. Let's actually talk about horizontal and vertical tangent lines. So let's find, maybe a question would ask us, where are all of the horizontal tangent lines? And there could be more than one. And so we are going to go ahead and take the y derivative, dy over dt, and we're going to set it equal to 0. So the derivative of y with respect to t was 12t. We're going to set it equal to 0, and we find out that at time 0, we have a horizontal tangent line. Now, if it asked us for the point where there's a horizontal tangent line, then we have to plug that time 0 back into our x parametric equation and our y parametric equation to actually produce the point that creates the horizontal tangent line. So just make sure you read your instructions carefully. Now we could have a separate question that asks us to find any vertical tangent lines. And so we will go ahead and set dx dt equal to 0. So we're going to take the derivative of x with respect to t, which was 16 times 2t plus 1, and set it equal to 0. So we'll divide that 16 over, and we have 0 equals 2t plus 1. Subtract the 1, divide by the 2, and we get t is negative 1/2. Again, that's the time that creates the vertical tangent line. So we can plug that time back into our original x and y parametric equations to get the actual point where that occurs. Now, a couple of notes here. We could have more than one t's that make these tangent lines. And so then you could plug those multiple t's back up in to get your multiple points. Because remember, these parametric graphs, plane curves, can do all kinds of weird, crazy things. Curve back around, do loops and all kinds of stuff. You could have a lot of vertical or horizontal tangent lines. The other thing to mention is that it really shouldn't happen at this point, but this will be an issue later in AP Calculus. Not necessarily with just plain parametric equations, but if you ever end up with the same time for a horizontal and vertical tangent line, that just can't happen. So for now, that probably would be a mistake, but it will be a scenario that we will encounter in the future. Now, there is one more thing that we have to be able to do with this. Maybe it would say find the equation to the tangent line when t is equal to 3. Well, just think about how you find an equation of a tangent line anyway. You're going to use point-slope form, right? And so for that, we need 3 parts. We need the slope, which in this case will be our derivative, and then you need a point. So to get the slope, we want to evaluate our derivative that we just found when t equals 3. So I'm going to go back up here. We're going to use the same equation. Our derivative was 3t over 4 times 2t plus 1. So that's going to be 3 times 3 over 4 times 2 times 3 plus 1, which is 9 over 4 times 7, which is 9/28. Then we can take that same t equals 3, and we can now use it to find our x1 and y1 by plugging it into the x and the y parametric equations. So let's do that. So we want to evaluate the x parametric equation at 3, and so that's going to be 4 times 2 times 3 plus 1 all squared. That's 4 times 7 squared. 4 times 49 is 196. Then we're going to do the same thing for y. That's 6 times 3 squared, which will be 6 times 9, which is 54. So our equation of tangent line will be y minus 54 equals our slope 9/28 times x minus 196. Of course, that 54 might be added over here if you're looking at a multiple choice answer. And so there you go. That's how we differentiate with parametric equations. We'll do a little bit more in future lessons, but there you go. Good luck.